How's it going, everyone? Cup of Science Joe here. Today, I'd like to talk about tidal locking. And to do this, I'm going to use the Earth-Moon system as an example. Let us start out with our moon. You may not have noticed this before, but you only ever see the same half of the moon in our sky. While it may appear then that the moon is not spinning, this is actually incorrect. The moon is spinning, but its rotational period also matches its orbital period around the Earth, hence only ever showing us one side. This phenomenon is known as tidal locking. While it may be surprising to learn, this phenomenon is quite common. In fact, all of our solar system's large moons are tidally locked with their planet. Usually, the larger the moon, the sooner it becomes synchronized or locked. This will happen outside our solar system too. Some binary stars are tidally locked to each other, and beyond even this, we're gaining evidence that there are planets out there that are tidally locked to their host star. How does tidal locking occur? One thing I think we should note in advance is that due to the law of conserving angular momentum, objects in space all love to spin. This is even more so when large-scale collisions occur. When two celestial bodies possessing gravity are in orbit, they will both place tidal forces on each other, with the larger of them holding the greater of the force. Let's go back again to the Earth-Moon system as an example. We believe that the moon was formed when a large impactor collided with Earth during the early years of its formation. This blasted large amounts of material out into space around the Earth, and with time, this material coalesced together into the moon. Now, at this time, it was spinning wildly and also would have been hot and molten. Its shape would change as it gets pulled at by Earth's gravity, distorting it into a football shape. Let's go ahead and have a look at an animation to help us out with this a little bit. As the moon spins, the part of it that is bulging will shift, but there will be a delay to this shift because it takes time for the material to rise and then fall again. This results in a tug-of-war type effect, where the bulge is always a little out of alignment with Earth, while also being pulled towards alignment by gravity. This bending and flexing released energy in the form of heat. As this process dissipated that energy, it slowed down the moon's rotation until a single spin on its axis matched the amount of time it took for one trip around the Earth. With no more energy to dissipate, and the spin rate no longer changing, the moon became locked in place with Earth. What is the moon up to now? Well, all this energy the moon was shedding had to go somewhere. The answer to this is into its orbit. This has caused the moon to slowly drift away from Earth over time. When the moon formed, it started about 17 times closer to the Earth than it is now. That's a difference of around 14,000 miles away to now being around 250,000 miles away. That is a jump right there. In fact, if the Earth and the moon could somehow survive the death of our sun, in about 50 billion years, the moon would drift far enough away to also tidally lock the Earth to it. But I don't think any of us, or even our solar system for that matter, are going to be around to have to worry about that one. I hope you learned something today, and I implore you to step outside tonight and look towards the stars.